The Sun, an average star, a structure over 1 million times larger in volume than the Earth, generating and releasing tremendous amounts of thermonuclear energy. Our understanding of the behavior of this solar energy, the plasma flow, and the mass and thermal transfer that occurs is far from complete. We have certain theories associated with solar behavior, but have never been able to look at the Sun in sufficient detail to verify these theories. The Skylab space station's 3 manned missions during more than 9 months of operating life in space offered a wonderful opportunity to collect data that might prove or disprove these theories.
The Skylab program uses much of the Apollo hardware. For instance, the laboratory will be launched by the first 2 stages of the Saturn V vehicle shown here in its Apollo configuration. Within the space that would normally be the rocket's 3rd stage, most of the Skylab components will be assembled prior to launch. 3 of the smaller Saturn 1B vehicles will be used to transport 3 separate crews to the laboratory. The Saturn 1Bs will be launched from Pad B of the Saturn V launch complex. Being smaller, they will be mounted on and launched from a pedestal. All vehicles and payloads will be assembled in the huge Vehicle Assembly Building and transported vertically to the launch pads. The Launch Control Center, built for the Saturn V, will be used for all 4 launches. The laboratory will be launched first and placed into a near circular orbit at 235 nautical miles altitude and a 50-degree angle with the equator. This high angle permits Skylab to fly over all of the United States except Alaska, and in fact over about 75% of the entire surface of the Earth. After reaching orbit, the protective fairing is jettisoned. The craft is stabilized, and the telescope mount is rotated to point the telescopes toward the Sun. Solar panels are folded during launch, then deployed in orbit to convert sunlight into electricity to operate the telescopes and provide power for the rest of the laboratory. Next day, a Saturn 1B is launched with the first 3-man crew in an Apollo spacecraft adapted to this mission. The spacecraft is maneuvered into an orbit that permits rendezvous and docking with the laboratory. The men transfer to the workshop and begin their missions. 28 days for the first one, 56 days each for the second and third. Skylab will fly unmanned between missions. The living areas and primary work areas of Skylab are on 2 levels within the orbital workshop. Using mock-ups, we can see some of the details. On this level, there are 4 rooms. This is a ward room where the men will eat and relax. A window will provide a spectacular view of the Earth when on Earth's sunlit side. It will be double paned with glass of high optical quality. Heaters will keep it from fogging. During off-duty hours, the men will enjoy reading, listening to taped music, to radio transmissions from Earth, and will communicate with their families. Food sufficient for 140 days of manned operation will be stowed prior to launch, most of it in these lockers. The food management area of the wardroom is similar to an earthbound kitchen. Special trays will warm the food, and the men will eat from them, much as do commercial airline passengers. For privacy, there are 3 compartments for sleeping. Sleeping bags have adjustable restraints. Since being weightless, the men will tend to float about. In 0G, there is no up or down. Garbage, waste paper, soiled clothing, and so on will be bagged and placed into a storage tank. This is the bathroom. Primarily, bathing will be done with a hand sponge, but other methods will be tried. Samples of urine will be frozen. All fecal matter will be dried. Both will be stored in containers and returned to Earth for analysis. The excess urine and water will be bagged and placed into the storage tank. The floor and ceiling are made of open mesh, primarily to allow for good air circulation. Specially designed shoes hook into this mesh to provide body restraint, since in 0G, without them, it is difficult to stay in one place. This is a mock-up of the airlock, which provides a 5.5-foot pressurized tunnel between the workshop and multiple docking adapter. In addition, as its name implies, it provides an airlock so that men can move outside the laboratory and re-enter without losing pressure inside. Tanks store the nitrogen and oxygen needed for breathing during the entire period of manned operation. Equipment and controls for keeping the air fresh and circulating are located here. Electrical power from the solar panels is brought here and distributed to the entire laboratory. The primary consoles and displays for the communication systems are mounted here. The main purpose of the multiple docking adapter, of which this is a mock-up, is to receive the spacecraft that transport the crews to and from the laboratory. The main docking port is at the end, and there is an emergency docking port on the side. But the docking adapter is also a workstation. It has a window of high optical quality for precise photography of the Earth, and will have instruments and controls for many Earth observations. The control station for the solar observatory is located here. From this station, an astronaut scientist will scan the sun, train the telescope mount, and record the sun's radiations. Approximately 50 scientific investigations will be performed during each mission. Here are a few examples that serve to illustrate their type and scope. At intervals during each flight period, the metabolic rate of each astronaut will be measured at rest and when performing a calibrated exercise on a bicycle ergometer, which records the energy being used, while a metabolic analyzer records the volume and constituents of exhaled breath. These tests will show how prolonged weightlessness affects breathing and measure the energy consumed by physical activity. Determining weight in a weightless world is a real problem. With no gravity, there is no weight, and normal scales cannot be used. But there is mass, and many of our biomedical experiments require its measurement. For measuring small masses in Skylab, this device will be used. Using a known mass, the device will be calibrated in flight and later used to determine the mass of food intake and of excrement. The object to be measured is placed in a holder held by a rod suspended on a spring. By releasing a lever, a pendulum cycle is set up. The time of each cycle is precisely measured and is proportional to the mass of the object. The device is so sensitive, it can even weigh a postage stamp. This odd-looking chair will be used to weigh the astronauts. It works on the same principle as the small device, but the man sits in as immobile a position as possible, even holding his breath. In this experiment, the split seconds are monitored and displayed electronically. The time it takes for the pendulum motion is recorded, and from this, the subject's mass is calculated. The chair is restrained by a spring. Here, too, a slight mechanical push establishes a pendulum action. The greater the mass of the subject, the slower the movement of the chair. Before and after each mission, extensive tests will be made on each astronaut to determine body changes such as loss of calcium in his bones, deterioration of his muscles, changes in blood circulation and constituents. Extensive baseline data gathered in simulated Skylab conditions on Earth will be used to compare with actual Skylab medical findings on many zero-G reactions of the human body. From spatial orientation to motion sickness. Other biological investigations will be made using pocket mice and vinegar gnats to study the effect of prolonged weightlessness combined with the removal of the normal 24-hour day-night cycle to which all life on Earth is subjected. What is the mechanism that causes daily rhythmic changes in temperature, pulse rate, and other life processes? This equipment will be used to study the effects of prolonged weightlessness upon individual human cells. In the black box are laboratory instruments skillfully miniaturized for use on a spaceship. On the right is a regular Earth laboratory microscope camera and lamp. On the left, the Skylab equivalent takes up a small space inside the container. In one compartment of the compact box are two cameras with lenses magnifying 20 and 40 times, with lamps, 16mm motion picture film, and a motor to move the film in front of the lenses. The human kidney cells to be photographed are in two chambers at one end. At regular intervals, time-lapse motion pictures like these will be taken. They may reveal zero-gravity-induced changes in cell behavior, such as in the reproductive process. The living cells are fed nutrient pumped in through tubes. They will be returned to Earth for continuing observation. In the compartment on the other side of the container are two assemblies of biopacks, each holding thousands of human lung cells at normal body temperature. At preset times, the Skylab astronauts will operate controls to fix these cells in order to preserve them at various stages of their growth. All the cells, fixed and living, and the exposed film will be brought back to Earth, where individual cells will be carefully studied for any changes from the norm, for instance, in their chromosomes or metabolism. All life is influenced by gravity. By removing gravity from living cells, the simplest units of human material, scientists hope to find new clues to the nature of the life process. To learn more about the sun, extensive studies will be made during the entire Skylab mission. The Solar Observatory is the most complete ever placed in space. It includes a specially designed telescope mount that will point the telescopes precisely to selected areas of the sun and the gases that surround it, and hold the entire laboratory steady while the radiations are being observed and recorded. 8 telescopes are mounted within a cylindrical shroud that will have a liquid cooling system to keep the entire assembly at a constant temperature Through these telescopes, measurements of solar activity will be made simultaneously in different wavelengths, in white light, ultraviolet, and X-ray regions. Most of the data will be recorded on film, some on tape.
Dr. Tony DeLoach, chief of the Solar Science Branch at the National Aeronautic Space Administration's Marshall Space Flight Center, comments on the importance of solar studies to man.
All life on Earth is totally dependent upon the sun. The sun's radiation moves the Earth's atmosphere, creates the energy for our weather and climate, causes the waters of the oceans to evaporate and fall as rain. The sun's radiant energy is the source of virtually all of our energy resources. Without the sun, life could not exist here on Earth.
The sun's power is enormous. In 1 second, the sun radiates more energy than man has used since the beginning of time. Earth receives only about 1/2 of the sun's radiant energy. Yet, if we could collect and efficiently store and use the sunlight falling on the city of Los Angeles alone, it would supply us with more electrical energy than is now produced by the entire world. If we could better understand the sun, our closest star, we would better understand the myriad of stars in the universe in which we find ourselves.
The sun has both subtle and violent effects upon our planet. Plant growth and weather are altered by solar activity. Communications can be disrupted. Strong geomagnetic storms caused by large solar flares create auroras and can affect electrical transmissions through commercial power lines. If we could better understand the sun, we could then better predict its effects. And so, a new approach to the sun from Skylab.
Skylab, a solar observatory in space, placing an array of complex telescopes into an environment free of weather conditions and the screening effects of the atmosphere. Telescopes able to observe several solar features concurrently, such as sunspots, appearing as relatively cool, dark areas on the sun's disk. Their magnetic intensities are 10,000 times greater than that of the Earth and are often associated with energetic activity. The most remarkable fact about sunspots is that their number and area are not constant, but vary in an 11-year cycle. Solar flares, short-lived but vigorous bursts of light, accompanied by intense radiation in the X-ray, ultraviolet, and radio parts of the spectrum. A large flare releases the amount of energy a city of 3 million would use in 50 million years. Flares usually appear in the light areas bordering sunspots. Coronal holes, cooler and more rarefied gases in the sun's corona or outer atmosphere. Solar bright spots, seen in X-ray photos, scattered all over the face of the sun. Prominences, masses of cooler luminous gas condensed out of the corona or shot up out of the solar surface along magnetic lines. Coronal transients, great explosions hurling outward enormous amounts of material, hundreds of thousands of tons in weight, into the sun's outer atmosphere at speeds of up to 2 million kilometers per hour, reshaping magnetic fields and structural features in large parts of the corona. Thus, from Skylab, a unified study of the sun, from its surface to the outer corona, the atmosphere that extends to include even the Earth. Skylab had a cluster of 8 solar telescopes. One was designed with a disk to block out the brilliant light of the sun itself. Skylab scientists created the equivalent of thousands of brief Earth observations of a solar eclipse to study the sun's corona. Before, it was assumed this outer atmosphere was fairly stable. The changes occurred only slowly over long periods of time. But Skylab revealed a much more dynamic corona, with many more changes occurring at faster rates than was thought possible, including this huge bubble, threaded by a magnetic field and extending into the outer atmosphere, rapidly growing to almost the size of the sun itself. Another telescope scanned selected portions of the sun, recording extreme ultraviolet light from several layers of its atmosphere. These layers, lying above the visible surface of the sun, the chromosphere corona transition zone, and the corona, were scanned simultaneously and are displayed here using various computer-generated colors. In this sequence of ultraviolet photographs, a surge is shot out of the chromosphere and into the corona. By means of such time sequences, the flow of energy upward into the corona can be measured and balanced against the downward flow, allowing for the first time an accurate assessment of the dynamics of the solar atmosphere. For the first time, Skylab astronauts were able to take detailed data of the whole sun in the ultraviolet region of the spectrum. This picture shows the areas of the sun's atmosphere which are between 50,000 and 100,000 degrees Kelvin, at the time of an eruption that lifted this twisted sheet of flame off its surface. The eruption is one of the largest ever recorded and had grown to 40 times the size of the Earth when the photograph was taken. The X-ray telescopes were designed to study the evolution of the hot, tenuous atmosphere of the sun. Here is an example of a rapid change in structure. This picture was taken at the time when the major reconfiguration took place. At this time, the brightest area was the biggest emitter of X-rays. Its temperature was in excess of 4 million degrees and was perhaps 10 million degrees or more. Skylab studies of coronal holes, dark areas on the sun, show that they may be the source of the solar wind which extends beyond the planet Jupiter. Coronal holes may also have strong magnetic boundaries. As the sun rotates, these huge magnetic sectors sweep by the Earth, disturbing the upper atmosphere. There are indications that these disturbances correlate with the formation of low-pressure weather centers. Additional new information about the sun also came from ground-based solar observatories, such as this one at the Marshall Space Flight Center. These observations are being correlated with those of the Skylab instruments. Some Skylab principal investigators, whose experiments were among the major Skylab solar studies, comment on results.
The mission was the fact that by looking for a long time, 9 months, with temporal resolution of as little as a few seconds for very rapid events, we were able to watch the way that structures in the solar atmosphere grow, the way they evolve, the things that happen to them, and then finally the way that they dissipate and decay. This was something that we'd never been able to do before from rockets or from the lower resolution measurements that had been made from unmanned spacecraft.
Well, in fact, we're just at this point beginning to get into the analysis in great detail. There's such a wealth of data there that it's going to take many years to really appreciate what it's told us about the sun.
I think there are a few things that we have already seen coming out of the data. I think the importance of transient events for the corona, basically the dynamic nature of the atmosphere. I don't think anyone had really realized prior to the Apollo telescope mount flight on Skylab how active the atmosphere of the sun was. I think that one of the things we learned from ATM was the relationship between the structures and processes that go on in the solar atmosphere and the things that affect the Earth from the interplanetary medium. And this, I think, will prove, once we've understood what was going on there, I think this will prove very fruitful.
The whole area of solar-terrestrial relations, I think, will get a tremendous shot in the arm when we finally get the solar data put together and begin, indeed, to make the comparisons with the spacecraft that are in orbit around the Earth, and indeed with the correlations that one observes from the Earth's surface.
But even in spite of all these observations that have been made in previous programs and with the ATM itself, it's interesting how there's still so much in the way of new and exciting things that still remain to be done in the solar astronomy area.
Skylab solar astronomy has shown us a sun that is far more active, even violent, than we thought. In the next few years, Skylab solar astronomy will tell us even more about the sun, but also about our planet Earth, a cool island within the outermost layer of the sun. Skylab solar studies show our spaceship Earth in its orbit around the center of the sun, interacting with the solar wind, creating a wake extending beyond the orbit of the moon. Earth, man, and all life on Earth caught in solar forces and events we do not yet fully comprehend, but will one day. Skylab science and technology will lead to continuing solar studies in space, utilizing future space shuttle flights for a better knowledge of the sun, our solar system, other stars, the nature of the universe. Before this century ends, solar astronomers may unlock the secrets of the solar behavior, including the storage and transfer of thermonuclear energy on the sun, which will have vast implications for man's life on Earth. For the sun is our bridge to more than the stars. Skylab Solar Astronomy has shown us the value of the sun as a laboratory in which man may discover new knowledge that will affect all life on Earth.